Today we're going to be going over these three problems from the Educational Codeforces Round 145, rated for Division 2. So let's get started. So problem A is called garland, and essentially you have a garland consisting of 4 colored light bulbs. The color of the light bulb is Si. Initially, all the light bulbs are turned off, and your task is to turn all the light bulbs on. You can only perform the following operation any number of times. Select a light bulb and switch its state on. The only restriction is that you can't apply the operation to a light bulb if the previous operation was applied to a light bulb of a same color. And the first operation can be applied to any light bulb. So you want to calculate the minimum number of times to turn all light bulbs on, or report that it's impossible. So this problem is a pretty interesting problem, which is pretty easily solved when we just think about it. So let's begin. So suppose we consider rather than the actual values of the lights, the number of different possibilities. So since it's 4 different colors at most that we can have, we can essentially just represent our 4 colors as A, B, C, and 1 second. A, B, C, and D. And A, B, C, D. So there are a couple possibilities that we have. The first is all of the colors are the same. The second is 2 colors are the same. So, or we have 2 colors. So A, B, B, or A, and then B. The third is that we have 3 colors. This is A, B, C. And this is in fact the only way to have 3 colors. And then we have 4 colors. A, B, C, and then D. Now, this case is impossible. It's impossible to solve this because they're all the same color. So there is -1. That's our output. Now A, B, B, we can simply go through and just bam, 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 where the striking basically represents turn on. And so we can do that in 4 moves. A, B, we can do bam, 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 and then turn this on, and then bam, and then, or rather, sorry, let me repeat that. On, off, on. Right, that's one way to do it. So we can do like this, which would be 6, or we can also do this, which is also 6. In the end, for this one, to get them all to be working properly, you need 6 operations. For this case, again, very simple, we can just do this, right? So that is 4 operations. And for the last case, again, we can literally just go sequentially, bang, 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 and that will be 4. So that is it. Now we just need to check which of these cases the solution lies in. And once we know which case the solution lies in, we can output the correct response. So there are a couple of ways to do this. The way that I chose to do this was to input this as a string and map from characters to ints. So now I have a map which contains all of my values. So for instance, I could have A2, B1, C1, right? And what I'm doing here is I'm checking what is the size of the map. So if the map has a size of 1, that means all of the colors are the same, which is impossible. If it has a size of 3 or a size of 4, then we've already shown that, well, the answer is 4, right? The size of 3 is this case, the size of 4 is this case. And this is the size of 2, this is the size of 2, this is the size of 1, just to clarify. The tricky part is handling if it's the size of 2. And so the way I do that is I check if the first letter, if ma of first letter, which basically means how many times does this first letter occur. If the first letter occurs 2 times, then I'm going to output 4. So in this case right here, let me highlight this. So in this case, right here, and let's not use a red one, let's use a yellow one. In this case, what you can see is that if I select, no matter what I select, if I select an A, there's going to be two A's. If I select this one, which is also an A, there's two A's. Two B's, right? So no matter what letter I select, if it's 2, no matter what letter I select, it's going to be 2. But in this case, no matter what letter I select, it's either a 3 or a 1. So if the letter that I'm selecting is a 2, then I know that it must belong to this. So the answer is 4. Otherwise, it's 6. And that's it. That's how you solve this problem. So what we can do is we can move on to the next problem. So let's do that. So points on a plane. And let's just clear that. So you're given a two-dimensional plane and you need to place n chips on it. You can place a chip only at a point with integer coordinates. And the cost of placing a chip at the point x, y is equal to absolute value of x plus absolute value of y. And so this right here, this is called the Hamiltonian distance. The Hamiltonian, wait, first off, am I recording audio? Sorry, yes. So this is called the Hamiltonian distance. The Hamiltonian distance is basically, if you imagine the entire grid as a series of blocks, how many blocks far away is it, right? So this is just the Hamiltonian distance to the origin. But you need to place the n chips on the plane in such a way that the Euclidean distance between each pair of chips is strictly greater than 1, and the cost is minimum possible, right? So the cost here is the cost of placing n chips is the maximum among the costs of each chip. So let's tackle this problem. And we're going to do this by drawing a grid. So quick little grid montage time. Okay, so I got myself a grid, and what I'm going to do is I'm going to label the origin here. And I'm going to label the origin with this blue dot, right, like that. Okay, so now if I want to place one color, or one dot, one point, I'm obviously going to place it right on the origin. If I want to place 2, what I'm actually going to have to do is I'm going to have to place the 2 like this. And if I want to place 3, then that's going to be like that. These are the 3. If I want to place 4, then I'm going to place the 4 like this. So I can actually cover 4 points in a distance of 1, right? So 4 points only require a cost of 1. But what about 5 points? Here's the problem. 5 points can't fit in this distance of 1. And to make that clear, let me draw a boundary for all the points that are a distance of 1. This is what that boundary is going to look like. Boundary is going to look like this. All of the points inside this boundary are a distance of 1. And it might be easier to do this with 1. And then similarly, all of the points within this boundary right here are also a distance of 1. Okay? And all the points are also a distance of 2. All the points here are a distance of 3. Right? So I'm just drawing these concentric rings here so that you can see what the distances for each point is. And we'll do 4, sure, why not? All the points here are a distance of 4. And the center point is a distance of 2. Now, pause the video and verify for yourself that this is true, right? This is a distance of 1, this is a distance of 2, this is a distance of 3, this is a distance of 4. If I want to place 5 dots, my best bet, the way that I'm going to have to do this, is I'm going to have to place 1 dot here, and then place, so why don't we place it And then I can go ahead and do like 4 dots like this that are all a distance of 2. And in fact, in this 2 by 2, if I'm going to just consider this 2 by 2 right here, if I'm just going to consider this 2 by 2 right here, the one that's surrounded right there, then what I'm gonna actually do is I'm going to want to place my dots like this, all around the rim. All around the rim. And then I'm going to want to place 1 dot in the center. This will give me 9 dots. So I can fit 4 dots into 1. I can fit 9 dots into 2, right? That's good, okay. And I'm going to erase that for a sec. Because what about if I want to fit more than 9? I'm going to have to push myself up to 3. So we're going to plot all of you on the points on the border here. And once I do this, I'm going to go inwards 2 layers, and I'm going to push these points. And so how many is this? Well, this happens to be 16. So 4 takes 1, 9 takes 2, 16 takes 3. I think I notice a pattern here. If I were to do this last layer, wow, that is a horribly drawing. If I were to do this last layer, I would end up needing 4 layers for 25. So now hopefully you see the pattern. You simply want to take, if this is the number of dots we need, you want to take something related to the square root of n. In fact, 8 dots are actually also going to require 2, and 5 dots are also going to require 2. So what you'll end up seeing is that the exact formula that we use is the square root of n minus 1 floored. This is our answer. And so my solution for this problem uses this. Here's the solution. So I'm going to input n, I'm going to subtract n minus 1, right? And that's just doing this n minus 1. I'm going to take the floor of the square root of it and convert that to a long log. So that's my answer. And now, for some reason, because of floating point precision or whatever, I needed to do this small check if k times k is greater than n, k minus minus, and then output k. But if you use your custom implemented square root function, you will find much better or much simpler implementation than this. But I do think this is the best that you're going to get. So let's go back to our last problem, which is problem C. This problem is much more interesting of solution. So for an array A, let's denote its subarray AL R as the subarray, and then we just skip over that. And you're given 2 integers n and k, and you want to construct an array with exactly k positive subarrays, and then the rest of the subarrays have negative sums. And then there's some bounding on the values that A can have. And n, crucially here, n is less than or equal to 30. Okay, let's take a look at this problem. So the solution here is a bit hard to understand, but essentially, if I just form a bunch of consecutive positive numbers, how many subarrays are positive here? The answer is going to be, well, if I have n consecutive positive numbers, then I'm going to have n choose 2, which turns out to be equal to n into n plus 1, or n minus 1, divided by 2. And let me just double check that back real quick. Nope. I'm not going to have n choose 2. I'm going to have n plus 1 choose 2. Essentially, I'm going to have n into n plus 1 divided by 2. That is how many subarrays there are. So there's going to be 4 plus 3 plus 2 plus 1, right? Because I can have 4 of size 1, 3 of size 2, 2 of size 3, and 1 of size 4. So that's 10. 4 times 5 divided by 2 is also 10. This comes from having to choose from m plus 1 boundaries. And so I choose one boundary, and then another boundary, and then divide by 2 because of the way that permutations work. But essentially, this right here, this is the number of ways that we can get, the number of subarrays that we can get out of m consecutive positives. Now, what if we try to maximize the number of consecutive positives that we had at the start, right? So suppose k is equal to 17. If I have one positive, okay, that's going to give me one subarray. One subarray versus 17 subarrays. Let's add another positive. That's going to bump me up to 1 plus 2 subarrays, which is 3. If I add another positive, that's going to bump me up to 1 plus 2 plus 3 subarrays, which is 6. Add another 2. I'm going to get plus 4 and then plus a 5. Happens to be 15. This quantity right here is 15. So right now, I have 15 subarrays that are positive. I want 17 positive subarrays. So what can I do if I just suppose that the rest of these are a huge negative number, right? So to indicate that it's huge, I'm literally just going to put negative infinity. And I'm going to do that, I'm going to indicate that using a blue color, right? A really big negative, some really big negatives, right? And basically these are big enough, right? Negative 1,000, such that this is essentially all our array is, right? Because if we ever include one of these big negatives, then immediately the entire subarray sum is negative. That's the point of this having negative 1,000, right? Because just to motivate this, if you have a number which is negative 1,000 in your subarray, the maximum sum you're going to get is like negative 900 something, right? That's still way too negative. So these are big negatives, and then these are some positives. If I want to turn this into 17, what I can do is I can, okay, don't do that, I want this eraser. I can erase that, and instead of having that be a big negative, why don't we have it be some small negative? Okay, let's choose a smaller negative. Now this negative is small enough such that if I just do this, it's negative. If I do this, it's negative. If I do this, it's negative. But if I do this, it's positive. And the reason we want that is because if I do this huge subarray, it's positive. And if I do this huge subarray, it's also positive. If I can choose a negative number that satisfies that, right, such that this is positive, right, this and let me just represent that using the red color. This huge subarray is positive, and a simple way of writing it is this huge subarray is positive, right? And then naturally this one also can get tacked on. If I can find a negative number such that that's satisfied, but this is negative, if I can find that perfect ideal negative number, I have successfully added 2 subarrays with positive. So this negative number right here will contribute, this negative will contribute to positive subarrays, right? So that will bump me up to what I want, to 17. That will take me from 15 to 17. And the general idea, the way we generalize this, is instead of choosing 17 and 15 as these random constants, we let k be whatever. We find this value such that it's as close to k as possible, right? So we find a value, let's call it k prime. Or rather, we find a value m such that m times m plus 1 over 2 is less than or equal to k, but, big but, m plus 1 times m plus 2 is greater than k, right? So what this says is basically I use as many consecutive positives as I can. Now I've got some additional subarrays I need, right? So I use as many positives as I can. I've got as many of these red pluses as I can, right? I got red plus after red plus after red plus. Now I need how many more? I need, let's call it k prime. Need k prime. What I'm going to do is I'm going to handcraft, I'm going to pick out a negative value such that there are k prime subarrays that have positive sum using this. So basically this negative is going to be manufactured such that, say, k prime is 3. Then this is a positive, this is a positive, this is a positive, but this is a negative. Right? So this is a negative, this is a positive, this is a positive, and this is a positive. That's the subarray manufacturing, or that's the value manufacturing we want to do. The way you do this varies from implementation to implementation. The way that I chose to do this was to make each of the positive values be 2, and each of this negative value to be basically, well, this is going to be 2, and this is going to be 2, so I want negative 4 minus 1 is equal to negative 5, right? Basically, this value should be negative, so this one has to be at least negative 5, right? This negative has to be at least negative 5, such that 2 plus 2 minus 5 is negative 1. But if I add on another 2, then it's going to be positive. That's the manufacturing I did. And you can see that in my code right here, where I'm saying needed is k minus tot. So, well, let me back up here. Tot is the number of subarrays that we've currently generated, and I is basically m in this case. So this is just finding out what the proper value of tot in I is. And then I'm just outputting those positive 2's. Now, if I is not equal to n, then I'm going to want to output this specially crafted negative number. That's this green negative number here. And the way that I do that is I find the needed, which is k prime. And then, once I have my needed, I'm going to output 1 minus I minus needed plus 1. So if I have 5 positives, and I want to only have 2 more, 1 minus I minus k prime plus 1 is going to equal 1 minus 5 minus 2 plus 1, which is equal to, this is multiplied by 2, so let me just slap on it, times 2, right there. So 5 minus 2 plus 1, that's going to be 4, 4 times 2 is 8, so this is going to be negative 7. Now, if I set this value to be negative 7, right, if I set u to be a negative 7, then what's going to happen is negative 7 plus 2, alright, that's green, negative 7 plus 4, green, negative 7 plus 6, green, but negative 7 plus 8 is going to work, and this is also going to work. So that perfectly manufactures the 2 that I need. This can be done, you can find these formulas through some trial or error, which is what I ended up doing, just trying out, okay, I've got my sum here is going to be 6, my sum here is going to be 8, I want to get my 7 perfectly manufactured, and I have these variables, how can I get a formula that works every time? Play around with it, you'll find out a value that works. And then these are my massive negative numbers. So that's how you solve problem C. Sorry if my explanation wasn't that clear. Hopefully the code helps you understand what's going on. And if it doesn't, let me know down in the comment section, and I can edit the video and update it so that it makes more sense. But yeah, that's basically it for this problem set, this problem series, whatever you want to call it. Problems A, B, and C. That's how you solve these problems. And just to show you the way that you solve it, like A, most of the work that I've shown on the screen here, I actually did on paper. And A took about like 2 inches by 2 inches of paper. And B took a little bit more. It took around 2 inches by 5 inches of paper. And C took the most amount of paper. It took around 4 by 4 inches of paper. But these are not a lot of paper-intensive problems. In fact, most of the problems you'll see aren't really about how do I plan out my exact algorithm. Most of the problems that you're going to see are really trying to get the crux of it, and then from there it's pretty easy. So it's not like how do I combine 7 different algorithms into one cohesive thing. No, most of the times, at least for div 2, A, B, and C, it's going to be what's the trick to this problem? What's this one thing that I should know that makes this problem trivially easy? So for problem A, the thing that you needed to know was, well, just the mapping states, right? That's what we found here. These mapping states that always hold true. For problem B, which is, well, let's navigate to it, that was the fact that, well, when we did some trial and error here, I did not mean to do that. When we did some trial and error here, it's the fact that you find that, oh my god, you can fit square numbers. I could fit 4 in a size of 1. I can fit 9 in the size of 2. I can fit 16. It's that finding that square number, that n to the power of 2, and in this case, which turns out the square root of n minus 1 floored. It's finding this that breaks the problem and makes it really easy. And lastly, for problem C, it was realizing that we only need a certain number of positives, and then we have one negative and the rest of them just are irrelevant. Realizing that you can turn turn a series of positive numbers into the desired array was the critical part of this problem, in my opinion. So yeah, hopefully that makes sense, and hopefully this has been helpful. If it was, please leave a like down below, and if it really helped you out and you want to see more, also hit that subscribe button down below. And yeah, that's pretty much it for this video. I will see you guys in another one.